Am I audible?
Go ahead.
Shall I start? Oh, yeah.
Everyone can see the slide.
Good morning, everyone. Thank you for this opportunity to talk today. Today, I'm going to talk about categorical structures to welded tangles. This can be seen as an analogous study to the well-known classification problem of planar algebras. And I'm from University of Melbourne, and my supervisor is Dr. Marcy Robertson. So in next 20 minutes, I'm going to cover two major points, and they are I'm going to talk about virtual tangles and circuit algebras that we are going to see through tangles and planar algebras, and eventually learn an alternative definition of wheeled prop, a monadic definition using directed graph. And once we build this machinery, I'm going to talk about the final result relating circuit algebras to wheeled prop, and eventually going to conclude what I wanted to say. And let's start with tangles and planar algebras. So what are tangles and planar algebras? So in easy words, categorically speaking, tangles are nothing but a kind of autonomous monodal category, and they also form a colored operand. So as the picture suggests, the picture on the left shows its categorical description, and picture on the right shows an object in this operand. So let's talk about this picture first. So in this category of oriented tangles, the objects are words on pluses and minuses, and the morphisms are isotopy classes of these braid-like strings. So please note that these are not only braids; these are sort of generalized braids where free-floating loops are allowed. So in this picture, this orange loop, we are allowed to have those loops, and we are also allowed to have strings which starts from source of a morphism, like the blue one, which starts from negative and it goes into the same source object. So this is allowed, and the autonomous structure, that means the dual of an object in this category, is defined by writing the objects backwards and changing the signs. So that's how we define the dual in this category. And this category is very interesting. It was studied by Torive, and this categorical study of oriented tangle finally led to the quantum invariant theory, and Jones polynomial were the result of this initial study. And this category also forms an operand, where the picture on the right represents an object in this operand, where this object corresponds to this this picture on the right, where we insert a disk at the places where intersection is taking place. So we have 4 intersections, and we have 4 disks on the right, and the composition is defined by similar to the composition in the little disk operand. So with that composition and this type of little disk pictures, it forms a colored operand, and they are important. So the point of this slide is to basically tell you that tangles can be seen categorically, and they can also there is also an operatic view to it. And
Away from this desk.
yes, now we are ready to talk about virtual tangles. So virtual tangles are generalization of tangles. That's how we can see it. And before we talk about virtual tangles, let's see what are virtual nodes and virtual crossings. So the picture is quite evident. So when we see knots on thickened surface, so it's the red knot is, so for in this particular example, this red knot is on solid torus. And please note that this dotted part of the knot is coming from behind the torus. So we also want to capture that information. And whenever the knot from front crosses, or at least it appears to cross from behind, the knots coming from behind, we want to capture that intersection. And to do that, we put a little circle at the places where this sort of intersection is taking place, and we call them virtual crossings. So these are called virtual knots. And similarly, if we see tangles on thickened surfaces, we call them virtual tangles. And for example, they are important because they also have symmetric monodal structures, and they also have a universal property. And this was recently studied by Adrian Brochure. And the idea of his study is to sort of provide an analogous study to the categorical study of oriented tangle initially did by Tribe. And the picture at the bottom, this is a typical morphism in the category of virtual tangles. So objects are the same as the objects in the category of oriented tangles. These are non-associative words on pluses and minus. And the morphisms are generated by 5 elementary morphisms in this categories. They are overcrossings, undercrossings, virtual crossings, and these cup maps represented by units, and cap maps represented by countal maps. And this blue color in this morphism, it represents the underlying surface. So these are some higher dimensional surface, and yeah, and these arrows are nothing but usual tangles. So virtual tangles are related to circuit algebras. So before looking at its relation, I chose to first sort of briefly talk about what are circuit algebras. So in easy words, circuit algebras are family of vector spaces indexed by some finite subsets A in, A out. They can be any finite subsets, and they comes with the linear maps parameterized by wiring diagrams, and they can also be seen as an algebra over a specific operand. So like planar algebras, we can see them categorically, we can see them operadically, we can view circuit algebras in the same way. And when we say linear maps are parameterized by wiring diagrams, this picture tells you why. So there is one correspondence between these linear maps and wiring diagrams. So what we have done, we have replaced each disk A1, A2, A3 by vector spaces in the source. And the target vector space is nothing but the big unit disk, which is A0. And these indexing set A1 in, A1 out, they represent the incoming strings and outgoing strings from my little disk A. So that's how this wiring diagram, this picture captures the linear maps in linear maps in the circuit algebras. And just to tell you what are wiring diagrams are nothing but planar tangles, as we saw in very first slide, except that in wiring diagrams, these strings, they are allowed to cross each other. In planar tangles, we are not allowed to do that. We are allowed to do that partly because we want to relate it to virtual tangles, and in virtual tangles we have this virtual crossings, and these sort of intersections, they sort of in some sense represent virtual crossings. And let's quickly see the relation. And the relation is the following. So virtual tangles have circuit algebras representations. In particular, these are circuit algebras with 2 generators. They are overcrossings and undercrossings, and 3 relations. They are classical right master moves. So in virtual tangles, they also have planar algebra representation, but they are not elegant because in that representation, we'll have 3 generators because strings are not allowed to intersect. So we'll have to add this extra virtual crossing as part of the data of generator. And then because we are adding virtual crossings, we need to capture or we need to add 3 more relations, which we call them virtual ride master relations. So that's the one part of the story. That's how virtual tangles have circuit algebra representation. Now we'll begin the second part of the story, where this is the first step to define monadic definition of a wheeled prop based on directed graphs. So let's quickly see what are directed graphs. So here I avoid to give the technical definition of graph, but to choose an example, and then we'll see how the machinery works. So this graph, a graph is nothing but a quadruple where flags are half edges and IGs are involution maps, VT of G are vertices, and pi Gs are they are fixed point free involution maps. So the picture on the left, this is an example of a graph where you can see that all the AIs and PIs are flags, and the vertices of G, it partitions, this is a partitions of flags. Each partition represents a vertices. So for example, here A1, A2, A3, if you see this partition, these edges represent the vertex 1. And A5, A6, A7, A8, this represents the vertex, vertex B. And since vertex 3 doesn't have any flags, so we have this empty set here. And this involution map, it will have some fixed points and it will have some non-fixed points. And this pi G, it acts on only the fixed points of involution map. So without going into the technical detail of graphs, it's like that's how it looks like. And these AIs on the boundaries, they are the boundary of G. And these free floating loops, P3, P4, it represents a free floating loop. So we have this convention that we don't give directions to these free floating loops. So they can, because it doesn't really contribute to the data. So yeah, we just don't give it a direction. And the figure on the right represents a graph substitution, or the categorical composition in other words. And it's quite easy to see. If you want to compose 2 graphs, you simply replace the graph into another, provided that the direction of incoming and outgoing edges they matches. So yes, so this is the vector graph, and now we are ready to sort of talk about wheeled props. But before that, we'll take a moment to define 2 important categories. And the first one is this, and the second one is this. So let's see what is this category. In this category, the objects are the directed graphs, those sort of indexed by incoming and outgoing edges. And morphisms are nothing but bijection of flags. And these bijections, they preserve all the vertices, involution maps, directions, and labels. If the directions are different, then there is no bijection. So the direction has to preserve. And then another category is the category of S-by modules, where S-by modules is, to briefly tell like what are S-by modules, they are the collection of vector spaces which has right symmetric group action and left symmetric group actions on I's and J's. It's basically permuting the family of vector spaces. And morphisms are linear maps. We have vector spaces, so it's a natural choice to have linear maps within them. And in particular, because we have this S-by module structure, so we want our this action, this SL cross SLJ to sort of preserve. So these are equivalent linear maps. And now that I have these 2 categories, I'm going to define this operation. We call it E decorated graph, where E of G is defined by, that means this is a bimodule where indexing set is labeled by graphs. So and because this graphs comes from the category, defined above, and because the graphs are indexed by incoming and outgoing edges, so these are in particular INJs in this case, and the decoration is simply defined by taking tensor product all over the vertices. And so yeah, using all these ingredients, we have this lemma that this category this category of SMI module, it actually forms in monad, and this category sorry, I mean this endofunctor, it comes with natural transformation and all. So I wanted to avoid speaking like all the technical data. It requires some construction. So so yes, and that's how this endofunctor works. It sends each vector space as part of my data of S by module to the colimit. So, and note that this is the graph decoration. This is not a usual. It just does not send any bimodule to itself. It sends a bimodule to the colimit of its graph substitution. So that's how this category of graphs and bimodules, they are sort of all related.
Could you give an example of an S-by module? Or like, or just repeat the definition?
Oh, so I said it's you can think them as family of vector spaces where they are indexed by some finite subsets as in INJ, and the action, the left action of a symmetric group on L, it sort of permutes the I vector spaces, and the right action permutes the like the J vector spaces. The positioning is important because they are in the category of graphs, they are labeled by incoming vertices and outgoing vertices. So if you change the position, your incoming strings might get converted into outgoing strings. So this is why this indexing set and actions are important.
And what is early IJ? Like
Sorry, curly?
IJ.
Yeah, so this is some countable set of alphabets, because we can't have infinite sets, right? Because we want to capture, like we want to have finite numbers of edges and vertices. Yeah, so what is a wheeled prop? Wheeled prop is nothing but the algebra over this monad in other this monad in category of S by module, that is a pair S by module and a structure map. So this like unpacking the definition of algebra over a monad. And now we are ready to talk about the final result, which is a circuit algebra has a wheeled prop structure. Every circuit algebra has a wheeled prop structure, and the proof is basically divided into, like, the proof is based on three important observations. The first one is that every circuit algebra E comes with a sort of a free comes with a like a default S by modules, where each where the labeling set, again, like I mentioned, like INJs are not random, but they are sort of decorated by incomings and outgoing strings, because every like vector space in circuit algebra data, they correspond to a disk, and each disk has incoming and outgoing wirings. So that's how the labeling works. And each wiring diagram, since each wiring diagram induces a linear map, so every circuit algebra has a, like, it can be seen as an algebra over an operand. So we use that this fact that each wiring diagram gives me this linear map here, this particular, and here yeah, and the structure map is obtained by, like, defined by this commutative diagram, where this this red arrow is it comes from the wiring diagram data, and the green arrow comes from the definition of colimit in this context, where, I mean, a colimit is a vector space. It comes with this map from a decorated graph to its colimit, and the commutativity of this diagram is comes from the universal property of colimit. So I have I've got an S by module, and I've got a structure map, and the commutativity of diagrams using multiplication and units, they are ensured by the previous lemma that we talked about in the last slide. And to sum up everything, I think this summarizes our proof. So everything is based on that, based on the fact that wiring diagram has one correspondence with directed graph, and the process on the left represents how we get virtual tangle and its circuit algebra representation, and the process on the right represents how we get a definition of wheel prop from directed graph. We started with directed graph, we build a category out of it, and then we use the category SY module. We combine them together to build a monad. Taking algebra over a monad is nothing but a wheel prop. And then we use this fact that circuit algebra has a wheel prop representation, and every circuit algebra has a wheel prop structure, and virtual tangle has a circuit algebra representation. So in other words, virtual tangles they are wheeled prop, and this arrow, it doesn't work backwards because every circuit algebra cannot be seen as a virtual tangle. It's just a particular presentation. So the result that I presented today, it's a consequence of a much stronger result, which says that category of circuit algebras and category of wheeled props, they are equivalent. That means every wheeled prop will give you a circuit algebra structure, and every circuit algebra will give you a wheeled prop structures. So the arrow will work backwards diagonally, but not downwards. So that's what I wanted to talk today. The core is that every virtual tangles have wheeled prop structure.
Again.